thank Patrick, and first of all, thank for the organizer for asking me to contribute to the session. It's pity that I was not able to join physically. Hope that I will be in the institute in 2 3 weeks if everything is okay. So as Patrick say, I'm going to talk about a project, national project where we try to come up with identification, cancer cell identification, single cells using only biophysical characterization, and that identification has been say learned through statistical classification model. So as Patrick say, I am statistician. Let me skip the presentation I was trying to do. Okay, so like I said, the project we are working with a team with different disciplines from physics, biology, from mathematics and computer science. And the name of that project is CytoMems. And we try to come up with the first mem device able to classify in real time or identify in real time cells using this MEMS device. I will talk about it later on. So pretty sure that characterization of cells are usually done in a biological point of view. So with this new project, the global aim is to like correlate the biological properties that are well known to physical or mechanical characterization using a MEMS device. So why using the biological properties of cancer cells? So it's well known now since that that biological properties may be very promising to detect cancer cells, so to identify them, like as you see here with three different cell lines. We may see that in an average point of view that they are different. They have different biological properties, and using this information on the biological property and using kind of modeling, deterministic or probabilistic, so we may be able to identify and then for the global aim to predict the properties of the cell only using the electrical or mechanical or both of them characterization. So for that, say so this MEMS device here, we have now in the center in Lille that Patrick and also Nikos visited. We are now able to characterize in a physical point of view, but also in a mechanical point of view, single cells. And this gives a lot of information regarding here. If you see the three cell lines, we have here MCF7, some NU937, that if we compress this cell having different kind of frequencies, then we may have electrical signal and also mechanical signal. And in one point, the electrical signal using different three kind of frequencies are able to give information on the cell size. For instance, the low frequency in electrical point of view is able to characterize the cell size. The membrane capacitance is related to the medium frequency, while the cytoplasmic conductivity is related to the high frequency. And if we are interested to the stiffness, then the mechanical information here is able to let's say count the stiffness information. So usually when I began discussing with the colleague in physics and biology using this characterization, so using the signal, the electrical one and the mechanical one, then they sum up this information and take the maximum, what they call the peak to peak, the maximum information on that curve and the maximum information of the curve, and using statistical, let's say, multivariate classification modeling in a statistical point of view to be able to, let's say, discriminate and highlight the features or the variable that are linked to the type. And then I discovered that after discussing with them that in fact, their, let's say, vector valued or finite dimension data they have come from the signal. And since I am specializing in studying data in form of curves, shapes, images, etc. Then I try to see if using the whole information maybe may give an added value on the identification. So that's why we come up with what we call functional data analysis. I will explain what I mean by functional data analysis. So to be more precise, so using the electrical characterization and the mechanical characterization, it is the kind of data. If I zoom in here, this is how the five, let's say the three signal. Let's take like the real part. We can also have the imaginary part. If we take the three frequencies in the electrical measurement, the imaginary and the real and the imaginary part, and then also the mechanical information. Here we have let's say seven kind of data. Okay, and if basically in time series analysis, so we discretize the points, then we may be in a finite dimension, like 7 multiplied by the number of points here. It may be high dimension somehow. But if you take the maximum, like they usually did, the peak to peak, then you have only data set that be modeled as observation of random variable taking values in R7. Okay, in that case, the classical classification method was doing somehow good, was doing a good job, but as we're gonna see at the end of the talk, that taking the whole information here, the whole information on the curve, and modeling the data as functional, what I call functional random variable, may be really interesting and added value. So let's say in a general point of view that we characterize electrically and mechanically using the MEMS device, single cells. Let's take three or two groups. Let me just give example in two groups, aggressive or not, or metastatic or not cells. And like I said, if we sum up the curves, if we sum up the signal to the maximum value, then we can have the optical size, for instance, that is single value, the stiffness, viscosity, etc. So we can have some vector values data. So these are summaries of the whole signal. If you take the whole signal, then we're gonna have multivariate. What I call multivariate is several functions here, like the amplitude, the viscosity, etc., and the stiffness that is related to the mechanical characterization. So stopping here at the biophysical characterization, okay, we can just stop here and do some modeling, try to have a best model that highlight the data that are related to the cell type. But as we all know that the biological property and the image of the cell when compressing them has some information, and that information may be also used to the global aim of classification identification cells. So if in addition to the biophysical characterization, so if you add the images and biophysical properties that are well known to be correlated to the type, then we may have several kind of data sets of several dimensions taking values in different spaces, etc. So like here we have images, we have real values, we have functions, several functions, etc. So how can we combine all these several type of data to develop a statistical classification, or if you want, a regression and prediction method to being able to identify a say type. So for that, we need to, let's say, project or span all these data sets to the same space, because if they take values in different spaces, then we might come up with several classification or a single classification model using, for instance, PCA. Let's just take an example of PCA. So here, let me just focus on the biophysical properties, even if the combination of the biophysical properties, even if the combination of the biology and the physical properties and mechanical are also understood. So if we use all the information, so all the signal that come from the MEMS device, so and we let's say, model these are what we call functional data analysis in an area of statistics. I don't know if everyone is familiar with functional data analysis. That's why I will take like 2 minutes to explain what is functional data analysis. This is somehow, say, very high and infinite dimensional data. Okay, so even if in a functional point of view, we can do very beautiful mathematics, define random variables, expectation, and whatever we have in the multivariate setting. We know that in practice we have raw data. So with the data we have are raw data, even if we, let's say, smooth them to have function, etc. And this raw data, if we think about the image, the cell signal, electrical, mechanical, and then the maximum, the summary we have from the signal. If I put all of them in this variable, this bold xt variable, okay, where t is also multivariate, so it may be, let's say, xt1 is like the real signal of the low frequency electrical measurement, for instance, and T1 may be the time, the compression time. Okay, let's say XT2 is the image. Okay, T2 may be maybe 2-dimension or 3-dimension. So in a general point of view, I can define here a random variable xt that each component is state value in a different space. Okay, like xt1 may be coming from that space J to S, where S may be R. Basically, it's a curve. It may be a sequences. It may be images, surfaces, something very complex. So that xt may be defined as a functional random variable. Okay, in a complex way. Even if I'm gonna simplify it in a particular case, I will show you. So that is what we call in the area of functional data analysis or functional random variable. Okay, and to make it simple, let's say we take, like, if I go back a little bit, we take d equal to 1, like we have only one function. Okay, one function, and like I said, in practice we have only raw data, like a matrix, the time point where the curves are observed, and I is a single cell. Okay, so to be able to do, say, to write the model in a functional point of view, then we need to transform the raw data to functions. Okay, then we will support, let's support that the xi we have so much time point that we can consider that each curve comes from a functional random variable or stochastic process. Let's say stochastic process taking values in a functional space. Okay, how a very classical case in functional data analysis support that xi is square integrable. So the functional space is L2T, where T is the time domain. Let's say 0, it may be 0T, for instance, or 0, 1, something like that. And usually when you work in this kind of functional space, then we use basis extension like spline, Fourier basis, or using principal component analysis, doing spectral analysis based on the covariance operator. So for now, like I said, here we simulated data from Brownian motion. You see the classical raw data, and then now I will support that what I have are functions. So these are my data I'm going to work on, and we know that these data take values in an infinite dimensional space, like the space of square interval function on the time domain we are interested to. So in functional data analysis, what we call, and simplify the definition I had before, what we call a functional data, or it's a stochastic process, okay, that take values in a functional space of usually infinite dimensions. So x is now xt is my functions, and the basic one I'm going to use in the example is a curve. It's like the electrical curve or the mechanical curve. Okay, and then all the data set we're going to have from the cells we compress from 1 day to using 3 or 2 cell type. So observation from this functional random variable we have here. Okay, and this is rather a new, somehow new. It has like 20 years of more than, a little bit more than 20 years since the apparition of functional data analysis. Okay, and usually that in statistics, when we deal with random variable in R, okay, so it's very easy to compare two cells, two individuals, okay, using the classical Euclidean distance. So in a product, if we are in a vector value case, then it's also very easy. But in the case of function, let me take the simple example of square integrable function, but it may be a metric space or any Banach space or more. Then the usual way is to use this scalar product, and with this scalar product and norm, the L2 norm, then we're able to do the spectral decomposition and do PCA, and now reduce the infinite dimension to finite dimension by truncating in the spectral analysis. So let me remind that what the global aim here is to, let's say we compress cells from different cell lines. We don't know, let's say at the first beginning, we don't know the cell lines, okay? We compress them and then we classify, and we want it to be closest to the real situation, okay? So let me take the example of two cell lines, okay? Two cell lines, that's why the binary here. And so we aim to classify, we have two cell lines, and we aim to, let's say, build a model also that permits to select the variables. So the electrical measurement and the mechanical measurement that are able to classify. Okay. So why stratification here? Why stratification? Because usually, as you know, in epidemiology or biostatistics, it may be helpful sometimes to stratify. So not taking a random sample, okay? Like if you have two cell lines and then one of the cell lines is very rare, or two cancer or two disease, one of them is very rare. So if you sample in an arbitrary way, then you may have a sample where all the data are coming from one type. Okay, and then you are not able to estimate or to predict the other type. So in that case, doing stratification may be helpful. Like let's take the simple case of case control studies. If you do that, and then you use the, let's say, the basic and well-known general linear regression model for the classification, then if you ignore the fact that the sample is not random, then you are making a bias. Your data, your model going to be biased, and this is well known in biostatistics and epidemiology in the multivariate point of view. So when we began working with this collecting that project, so there was no statistical model available in the literature permitting to let's say to model functional data and binary output. So the output is Y, the two kind of cells, okay? Let's say U and MCF7, and the covariate, what we call the covariate, or the input are the mechanical characterization, the mechanical signal, and the electrical signal altogether, or only one of them to be simple. Okay. So the first thing we did, so was to extend what was done in the multivariate case to the functional case, taking into account the fact that the data are valued in a space with infinite dimension. So how did we model that? Let me take the simple case where, like I said, we have two type of cells. Let's say 0 and 1. Let's say 1 is the cancer and 0 is not cancer. And then let me take only one function to simplify, but we can take several functions here. Let's say X is the round variable related to the mechanical characterization, that is able to have information on the stiffness. Okay, and that X take values in a Hilbert space here, I suppose to be L2C. So what we want to, the model we are interested here is the extension of the classical model, the GLM model, okay, where we have the logistic model, the probing model, C-log, etc. In other words, we are interested to predict, to estimate, or to model the probability that Y is equal to 1, let's say, the cancer cell, giving the mechanical characterization. based on two parameters we don't know when to estimate, alpha star and theta star. In a usual linear model, usually theta is valued in R or RD. Okay, so in that case, since X is a function, so theta had to be a function. So this probability is modeled like phi. Phi is a cumulative distribution function. Let's say phi may be a logistic model or the probing model. If phi is a Gaussian cumulative distribution, then we have the probing model. So this is the model we wanted to estimate. So here I skip a lot of details, but not using a random dump. Okay, not taking like a prospective study and random dump. Here we have two population of cells, cancer and not, and we stratify in each population using, like say, Qi is the probability in the whole population. Let's say it's the probability of the cell in the population to be cancer cell. Okay, if I is equal to 1. Okay, and the other one is for 0. Okay, so usually we don't know this information. We don't know in the population the exact probability of being sick, for instance, or the cell being cancer or MCF7, etc. While H is the probability according to which the stratum, or according to which we draw a sample from the subpopulation. Okay, this we have to choose it. Okay, this may be like you take 50-50. Say 50 in your example, you have 50% of cancer cell and 50% of non-cancer cell. Okay, this has been given, but that one is usually not known, but we can estimate in non-probability, for instance. Okay, so so we come up with a maximum likelihood estimator. Here I name theta hat t. So theta hat t now is based on a truncation parameter Pn going to infinity with the sample size. So n is the sample size of the cells, and a certain percentage is from cancer cell, and the other one from the non-cancer cell. So this function here, so I skip a lot of detail because you don't have time. This estimator here, let's say it's an extension of the well-known maximum likelihood you know for the logistic regression, for instance. Okay, so the functional analysis method we use behind are based on spectral decomposition of the covariance operator. Here, since we are dealing with function of covariance operator, and then with that spectral decomposition, then we truncate, we take the first functional eigenfunctions here, and Pn goes to infinity when n goes to 0. And then we show that theoretical guarantee that functional parameter here is asymptotically normal, okay, based on some hypothesis on Pn. So Pn goes to infinity slower than the sample size, slower than n. But one of the most interesting things we showed that was the bias I was talking about before. So remember that here, these two parameters, H and Q, H is, let's say, the proportion of cancer cell you have in your sample, you choose in your sample, okay? And Q is the proportion of cancer cell in the whole population. We usually don't know, okay? And so if we, let's say, ignore the fact that the sample is not completely random, and then we estimate by basic usual maximum likelihood estimate, I name ordinary maximum likelihood estimate, then we're going to have this theta estimate, okay? But if we estimate like what we did here, taking into account the fact that the sample is not random but stratified, then this is the bias we're going to have. This is the bias we're going to have if we ignore the fact that the sample is not random, and then we take the usual maximum likelihood estimate. And as you see, if Q is not equal to H, and usually it's not the same, then you cannot delay that bias. The bias will be there. And in fact, that bias is more related to the constant parameter alpha star I showed you before. And that's why here, if it's very, very important in this kind of model, this kind of GLM model, in particular for the logistic model. So here it's only for the logistic. For the probing model, there is no bias, okay? not as much as that one. So in the logistic model, so we cannot delay that bias if the proportion um, of the cancer cell in the population is different to the proportion of the cancer cell in the sample, and usually the case. Okay, and that was really a very good finding we had. So let me now skip, since I don't have so much time, to the application and show you the result we had here. So let me choose here two kind of cell lines here, some and then NU937, and then we try in two samples of, here you have 140 for you and 102 for the sum. So here it's somehow more or less the same number of cells in the population. And then we can stratify or not. So here we use without stratification, because the two kind of cells we have were so very, very similar in the sample size. So using only the electrical measurement, okay, the three electrical measurement, low, medium, and high high frequencies. So we compare several statistical models like the LDA one, the GLM, etc., neural network, a bunch of them. And then let me show you here some of the results. So LDA was somehow very performant, even if it's not very complicated to model. And then here, as you see, using only the electrical measurement, though, and bootstrap Monte Carlo dumpling has been done also, meaning that we did the classification 100 times, and sometimes bunch of more than 100 times, like 500 times. Then we come up here with some of the Monte Carlo results to an error of 97%. Okay, this in the functional point of view. Okay, and in the multivariate it was more than that one. Now, if we incorporate, let's say, the stiffness information, remember that the mechanical property is adding an information on the stiffness. That information was not on the electrical part. So at the beginning of the building of the device, we were only able to have electrical measurement, because for the electrical measurement to move from the electrical to the mechanical one, then the device needs to be adapted regarding the size of the cells. So it was really hard to have that. It was in the technical part, I was not involved there. But once we come up with combining electrical and mechanical, then we reduce really significantly the classification error. And that was the first step that permit to really see the added value of using the whole information regarding the classification of cells. So just to summarize, so using the functional analysis, the functional data analysis, so we were able to have successful classification of or successful identification of the cell lines, here 2, 3. To be honest, it may be challenging if you have different cell lines. So here for 2, it's fine. For 3, even the result was not so bad, but we're still working on that to improve the results. And now we're moving to the let's say to the routine or to the practical point of view, where we try to come up with first of all a Python software. We're almost done with that for the classification modeling, and then to share with the community. And the last step would be now to move to the FPGA, okay, to have the real time classification of cell detected by the FPGA board. And this is the last step. We hope that we're going to be able to do it at the end of next year. And so that part was only in the statistical point of view. So we were doing the classification in a probabilistic modeling. Now with a new colleague in the team, Alexandre Foulin, Nikos know very well, we are working on combining the deterministic modeling and the stochastic modeling all together using the functional data analysis. And we already experiment this in a new project related also to cell characterization, but here to pairing, we are interested to the real-time activity measurement using pairing here 2 types of cells, cancer cells and not cancer cells, using LAMP, for instance. And this is an ongoing project where numerical analysis is combined to statistical analysis, and this is, yeah, so well, um, um, I hope a well collaboration that would be. So just to finish with some takeaway, um, so that project at the first beginning that started, let's say 5 years ago, with colleagues from medicine, from physics, from biology, permit us to come up with a new modeling with theoretical guarantees that were motivated by that cell identification problem, and that was really great. And then to the younger generation here, so I would really advise to discuss with other colleagues from other disciplines that may bring interesting questions, and our expertise on modeling may be useful. And that's it. Thank you for understanding.